So thank you very much for having me. I'd like to give a brief presentation on superfluid transport in the Unitary Fermi Gas. And I'm glad it's possible to do this remotely. I've actually used this opportunity to watch quite a few of the talks in this meeting, which have really been quite excellent. So my interest in this subject was somehow driven by two things. Number one, as I'll talk about, we've been spending quite some time on trying to understand transport in the normal phase of the Unitary Fermi Gas. And I've also lately been interested in trying to understand what happens to transport properties in QCD as you approach the phase transition. That's obviously not a phase transition to a superfluid regime, but to a chirally broken regime. But formally, there's a lot of similarities in the two subjects. Okay, so I was going to give a kind of brief and very, very general introduction to just fluid dynamics. Fluid dynamics, obviously, as we've learned over the last couple of years, is really a very beautiful theory. And indeed, it's a theory that's much more general than the sort of typical undergraduate version of it, which is that it's just Newton's law. So we're now applying fluid dynamics to many, many systems that are certainly not classical. And the general idea is summarized on this slide, which is that hydrodynamics is a very general effective theory for any kind of non-equilibrium many-body system, provided that the system can locally equilibrate. So the idea is that if you probe any kind of many-body systems, then there are really two kinds of excitations: those that correspond to densities that are not conserved and that generally just equilibrate on some microscopic time scale, and those that correspond to conserved densities. And here the equilibration time or relaxation time will get longer and longer the longer the wavelengths of that conserved charge is, because any conserved density cannot relax truly locally. It always has to propagate out by either diffusing or by propagating as some kind of sound mode. And so this means that if you look at very, very long wavelengths, then you will always be dominated by the conserved densities, and all the non-conserved densities will be in thermal equilibrium. And of course, historically, the system that was initially studied this way is just water, where the conserved densities have the density of mass, the density of energy, and the density of momentum. And indeed, for the Unitary Fermi Gas, these are exactly the same conserved densities. What I will also appeal to from time to time is that we can view fluid dynamics as an effective long-distance description that emerges from more microscopic descriptions. So again, in the case of the Unitary Fermi Gas, we can think of the microscopic description as being that of just non-relativistic point-like spin-a-half particle. Of course, that's already in some sense an effective description. The real system is, say, a lithium atom. But for my purposes, that's what I will pretend it is. So there's a non-relativistic spin-a-half particle just described by a Schrödinger Lagrangian. And then the system is so dilute that we can summarize all the interactions by just a single contact interaction governed by some strength C0. And of course, we can tune that one parameter to unitarity, where the scattering length diverges. Then in a suitable regime, if you go to longer distances, lower energies, you can describe the system in terms of quasi-particles. So that indeed is the case at temperatures that are significantly larger than the Fermi temperature. So you have a set of quasi-particles, and there's an equation of motion for these quasi-particles, and that's just a Boltzmann transport equation characterized by some kind of collision term. And this transport equation will describe properties of the system at energies or frequencies that are less than the temperature. If you probe even higher energies, then you do really resolve local behavior that requires the full Schrödinger equation. And now if you go to even lower energies or longer distances, then you will observe collective behavior that arises from many, many scatterings. And that's then summarized by the equations of fluid dynamics. And as we'll see in a little bit, formally, you can say that the regime of applicability is energies that are less than the temperature by an extra factor, which is eta over S, where eta is the viscosity and S is the entropy density. And you can already see from this that there's an interesting regime where if you consider strongly coupled fluids, where eta over S is of order 1, then in general, this kind of quasi-particle description is somehow pushed out, and the regime of applicability of fluid dynamics is unusually large. So here again, these are the hydrodynamic equations for an ordinary one-component fluid, non-relativistic, like the Unitary Fermi Gas, we have conservation of mass, we have conservation of energy, and we have conservation of momentum. And each one of those is associated with the conserved current. So the mass current, the energy current, and the momentum current. So in a non-relativistic fluid, there's an important word identity, which is that these currents are not all independent. In particular, the current of mass is equal to the density of momentum, and both of them can be expressed as terms of some kind of mass density and the velocity of the fluid. So this serves as a definition of what we mean by the velocity of the fluid. So then all we require is explicit expressions for the remaining two currents, the current of energy and the current of momentum. And so these will really, in principle, depend on microscopic details of the system. But since we're interested in long distances, we can expand them out in terms of gradients of the local quantities. So in particular, if you do this for the energy momentum tensor, which is the current associated with the momentum density, then there's certain terms that involve no gradients, there's terms with one gradient, and so on, terms with more and more gradients. And there's sufficiently many symmetries that the terms with no gradients are completely fixed in terms of the pressure and the density of the fluid. And all you need to solve the equations is then an equation of states, or a relationship between P and rho and comma and T. And at one derivative order, there's now some unknown quantities. These are generally known as transport coefficients. So in the stress tensor, there are generally two. There's a shear viscosity and a bulk viscosity. But as we'll see, in a scale invariant fluid like the Unitary Fermi Gas, it's really just the shear viscosity. Okay. So the shear viscosity can be extracted by relating it to a fundamental correlation function in your fluid. And one of the ways in which you can derive that is to study the so-called Kubo formula, which is the response of the fluid to an external perturbation. So the stress tensor couples to some two-index object, which is just a background metric. So formally what we can do, we can take a non-trivial background metric where we slightly perturb around a flat background. And of course, these days, you can imagine that there's an actual experiment where you send a gravitational wave perturbation through your fluid, but it also works as a just purely theoretical kind of construct. So we can study the response in the stress tensor to an external perturbation, and it just defines a response function. And you can, so you can take the fluid dynamic equations that I wrote down on the previous slide, you can replace the flat metric by a slight perturbation, and you can just study what is the change in the stress tensor, and that defines the response function. And so if you do that with the formula on the previous slide, the no derivative term, the response is just the pressure, and the one derivative term, the response is given by the shear viscosity. And so again, we imagine that we sit in the low frequency limit where this term is a small correction to the previous one. You can then see that there is indeed a criterion for the gradient expansion, which is that this term is smaller than the one before. So that means that omega must be less than P divided by eta. And if I express P in terms of the entropy density of the fluid, so dP by dt is S, so we can write omega is less than S over eta multiplied by T, which is the formula I wrote down previously. You can also derive from this a formal expression for the viscosity of the fluid. So you can take the imaginary part of the response, and then the term linear in frequency is proportional to shear viscosity. So again, that's known as a Kubo relation. So this whole formalism can be extended to a superfluid by taking into account that in a superfluid, we now have a spontaneously broken U1 symmetry and an associated Goldstone mode. And that Goldstone mode is like the hydrodynamic modes, in that the frequency of this mode will go to zero as we take the wavelengths to infinity. So that mode has to be included in the superfluid description. So the Goldstone mode is just a phase of the condensate, and excitations of it are most easily described in terms of gradients of that phase. So we define the superfluid velocity as the gradient of the phase in units of h bar over m. And there's an equation of motion for it, where again, everything is in principle completely fixed by symmetries, in particular the U1 symmetry, and where you see that the superfluid velocity is now not accelerated by gradients of pressure, but by gradients of the chemical potential. We must also now take the momentum density and split it into two components. So there is a part that's purely proportional to the normal fluid density and one that's proportional to the superfluid density and the superfluid velocity. And again, for the equations to close, we need some kind of thermodynamic, we need an addition to the equation of state, a thermodynamic relation that fixes the superfluid mass fraction. And at least formally, it's defined in terms of derivatives of the free energy with respect to the difference between the normal and the superfluid velocities. Okay, so once that is determined microscopically or measured experimentally, then again, everything is fixed. So the stress tensor and the energy current are completely fixed at the zero gradient level in terms of an equation of state, an equation for the superfluid mass fraction, then the various densities and velocities. So at the level of the dissipative terms, the expression for the shear part of the stress tensor is exactly the same as before, except that now it's all expressed in terms of the normal velocity only, and the superfluid velocity can in principle contribute to bulk viscosity. So there is one bulk viscous term that's exactly the same as the normal fluid, which is now multiplied by a coefficient that's usually called zeta 2, but there are three additional bulk viscosities, one that appears in the stress tensor and two more that correct the equation of motion for the superfluid velocity. So there's an extra term that involves two extra bulk viscosities. What is amusing is that if you impose conformal symmetry, so if you impose scale invariance, then three of these have to vanish, but one of them, this coefficient zeta 3, is in principle non-zero, even in a scale invariant system. Okay. So superfluid motion, of course, in these unitary Fermi gases has indeed been observed. So there was a series of experiments by Rudy Grimm, where indeed he observed not only normal sound, but also superfluid sound, so second sound. And again, if you just open Landau and Lifshitz, you measure the two velocities. Once you know the equation of state, that fixes the superfluid mass fraction. So he obtained these data, which are shown as the blue dots here. And in this image, they're compared to what the result is. The green line is the result for helium, and the red dashed line is the result for non-interacting, the theoretical result for non-interacting Bose-Einstein condensate. And as we saw earlier in this conference, there's now an improvement in a more recent measurement by the MIT group of the superfluid mass fraction, which indeed looks a little bit different, has smaller error bars, and indeed seems to cover a wider regime. So there are various limits in which one can try to estimate these transport coefficients, where indeed ideally you start from the microscopic theory. So this is something I already wrote down. I kind of view this, it's the many-body Schrödinger equation, of course, but you can view it some kind of non-relativistic field theory with the contact interaction, and the unitary limit corresponds to taking the corresponding scattering lengths to infinity. What exactly that means for this coupling constant depends a little bit on how you regularize the delta function in this interaction. If you do it in dimensional regularization, it actually literally means that one takes this coupling to infinity. That always sounds slightly disturbing, that the limit is somehow singular. The fact that it's not singular, you can make that more manifest by just rewriting this, sort of partially bosonizing this interaction, where you introduce some kind of dimer field phi and a Yukawa coupling to pairs of fermions. And then you see that 1 over the coupling constant becomes the gap for this dimer field. And so the unitary limit is simply the limit in which this gap disappears. Okay, so it's perfectly smooth. So one can apply kinetic theories to this at both very low temperature and very high temperature. And it's kind of TC, that's sort of no man's land from the point of view of kinetic theory. What happens at very low T is now you have this Goldstone mode in the system, the phase of the fermion condensate, and you can write down that's a good quasi-particle at sufficiently low temperature, and you can write down an effective interaction for that quasi-particle. And again, there are a lot of symmetries in the system that almost completely fix this. So the form of this effective interaction, so the fact that mu and phi dot have to come together, that's simply conservation of charge. The fact that phi dot and gradients of phi have to come together, that's just Galilean invariance. The mu to the 5½ is fixed by scale invariance. Then there's only one overall coefficient, that's effectively the Birch parameter. So once you measure the Birch parameter, the effective theory for these Goldstone modes is completely fixed. And then viscosity is simply dominated by scattering between these quasi-particles, where you somehow move momentum around. Now, the coupling is a gradient coupling, so it becomes weaker and weaker. And the way kinetic theory works, if you have a weakly coupled system, the viscosity will become very, very big because it goes as 1 over a cross-section. So at very low temperature, what kinetic theory would predict is a very strong growth in the viscosity as 1 over T to the 5. And this A is just some numerical coefficient that we in principle completely know. So there's actually no real free parameters in this other than the Birch parameter. At very high temperature, of course, the quasi-particles are just ordinary atoms.
Thomas, question?
Yes.
Oh, so this is Martin. Hi, Thomas. Just wondering about the 1 over T to the 5. So you're not including a 3 phonon, so like phi goes to two phis. You're assuming something about the dispersion there.
Yes, I will actually I'll come back to that in just a second when I think I will eventually comment on processes where you really need the splitting. So this is in a regime where indeed splitting is not relevant, and I assume it's totally linear, but I will say something about nonlinear dispersion in just a second. So in the very high temperature regime, of course, the quasi-particles are ordinary atoms. Momentum is being moved around by scattering between them. And that's a calculation that's been done by many people, scales as mt to the 3/2. Okay, so first observation is if you just naively take these two limits, the behavior at low temperature and the behavior at high temperature is really quite different. In particular, if you take this naive 2x2 scattering at very low temperature, that's super steep behavior that you wouldn't expect to somehow smoothly match the high temperature behavior. So experimentally, then one of the questions is, can that possibly smoothly match? And if it does smoothly match, can one somehow theoretically understand what exactly takes over in this regime? I have a small comment about thermal conductivity since it was mentioned the other day. So thermal conductivity in the normal phase is pretty straightforward. That's again just 2x2 scattering of atoms, and it gives a behavior that's again just T to the 3/2. Indeed, it differs from viscosity just by a constant factor, which is usually called the Prandtl ratio, which in the unitary gas is a simple number, something like 2/3 or 3/2. Now, in the superfluid phase, it becomes kind of complicated because number one, it's actually difficult to measure. You know, in a normal system, you just set up, as a theorist, you set up a temperature gradient and you watch how much energy flows. But superfluids, you know, and you do that in a regime where it's purely diffusive. That's what you mean by thermal conductivity. But in the superfluid, there's a very efficient convective process that moves heat around, which is kind of a flow of the normal fluid counterbalanced by a flow of the superfluid, that kind of, you know, backflow of the superfluid. As a result, it's actually very hard to measure, even though in principle there is a non-zero diffusive contribution, which you can try to dig out by carefully comparing the attenuation rates of different sound modes. So not only is it difficult to measure, it's actually also difficult to compute, because if you have a set of quasi-particles with purely linear dispersion, that doesn't contribute to thermal conductivity. And roughly that's because if you have a bunch of quasi-particles like this, what you mean by diffusive heat transport is that the fluid as a whole is not moving. It's just diffusion of energy, no diffusion of mass. But if you have a single quasi-particle where energy and momentum are linearly related, you cannot set up a flow where there is no momentum flow, but there is energy flow because they're just strictly proportional. And as a result, in kinetic theory, you only get this because there is indeed a slight nonlinearity in the dispersion relation, and as a result, phonons can split. So it's a combination of the phonon splitting rate and the nonlinear dispersion of the phonon. So at least formally you can do that calculation and you find an odd-looking temperature behavior. Again, it's controlled by the phonon splitting rate, which indeed is actually completely fixed by the Birch parameter. So this is this phonon splitting rate, but it's actually controlled by the Birch parameter. So at least in principle, we know what it is. But frankly, I sort of doubt whether that's truly observable. That seems like a very subtle process. Okay. So I wanted to just briefly, again, people have already shown some of these pictures. I wanted to just very briefly contrast to what happens in liquid helium-4, the important thing in liquid helium-4 is, of course, that there is a very important excitation that becomes crucial near TC, this Rotan minimum in the dispersion relation. And what that does is that now you have a quasi-particle in the system that effectively has a fixed momentum, almost independent of energy. And so what that does in a kinetic calculation is that there's a sort of background contribution to the viscosity of the system, which is almost independent of temperature. Whereas, even, again, in helium, the pure phonon rate is super steep, but there is a sort of background thing which is very smooth. And you'll see in a second, that's actually exactly what's seen in the experiment. So here's experiment. Of course, way back when, initially people just saw, you have a capillary flow, the viscosity seems to drop to exactly 0. But you do then a set of very complicated experiments. You see that took a long time, sort of 25 years to make it work. Typically, it's these experiments that involve a stack of disks, and then you watch the damping of a rotation pendulum. And if you do that carefully, you see that indeed at TC, there's a little bit of a dip, but then it's actually very flat just below TC before it starts to rise. So theoretically, this flatness, and the black line is indeed a theory curve, is kind of understood. And it's basically this Rotan contribution, which has a really weak temperature dependence. Okay, so here's now where we get to actual experiments in the cold gases. So that, in principle, the experiments by now go a long way back. So this is the original expansion experiments that were done by John Thomas's group at Duke, beginning in the early 2000s. Again, they caught my eye back then because it looked extremely similar to what is being done with the heavy ions. So you have this trapped cloud that's initially very, very deformed. So it has an aspect ratio of something like 40:1. You turn the cloud off, and the scale of these pictures is not changing. So you see that indeed in the long direction, it's essentially not accelerating at all. But in the short direction, it's accelerating very quickly so that eventually it becomes round. And then indeed, it becomes deformed the other way. And so the experiment you can do is just to measure these two radii. And the idea in interpreting them is to say that, look, at strong coupling, this is fluid dynamics. So what's accelerating the system is pressure gradients. The pressure gradients are larger in the short direction, smaller in the long direction. And what counterbalances this is viscosity. Viscosity will always try to equalize velocities, but pressure gradients are very anisotropic, try to accelerate in the short direction. And so the first picture is simply the fact that indeed you see this very large effect. The short direction becomes long, the long direction stays almost constant. If you look at the aspect ratio, then it starts very small, it becomes round, and then it goes deformed the other way. And indeed, you can see, so this is a set of experiments at unitarity. You can see that if you do the same experiment far away from unitarity, the result is very different. And at least at leading order, you can understand this as an effect of viscosity, that viscosity is trying to hold the system back. So this is a regime in which the viscosity is low, and this is a regime in which the viscosity is large. So the question is whether one can make that quantitative. And so in principle, that's very straightforward. You just have a large set of measurements of this type where the time evolution of this aspect ratio is investigated for a whole set of initial temperatures or initial energies. And that's plenty of information to, in principle, unfold the full density and temperature dependence of viscosity. But there is a problem that we struggled with for a long time, and it's the following, that so here's a sort of sketch of the initial density distribution of the fluid. It's a roughly Gaussian kind of cloud. It's dense in the middle. So in the middle, this is really a strongly correlated fluid. Hydrodynamics applies. But of course, on the outside, it eventually becomes very dilute. So you have these kind of Gaussian tails that have very few atoms in them. Now, you might think that that's really no big deal. Almost all of the energy, almost all of the mass is in the dense core. So maybe we can just ignore this. And the trouble is, if you just naively run a Navier-Stokes code, you cannot ignore this. And the problem is the following. So the velocity profile that develops is a sort of Hubble-like profile. The velocity is roughly linear in the distance from the center of the cloud. And if you just ask yourself what Navier-Stokes theory then predicts in a system like this, so the viscous dissipation has no factor of the density, and it's just strictly proportional to viscosity. And viscosity in the dilute limit, I showed you this kinetic result, is also independent of density. It's just a function of temperature. And as a result, you have this funny situation that you can sit way out here in the cloud. There's only, half an atom there. But if you were to believe fluid dynamics, there's a finite viscosity only controlled by the temperature of that 1/2 atom. And the velocity field is not small. So it actually dissipates a lot of energy in a regime where there aren't any atoms. Okay, so that's obviously not right. Now, there's nothing fundamentally wrong. It just simply means that the dilute corona is not a fluid. It's purely ballistic motion. But it raises a theory problem, which is how to couple the motion of the dense core to this kind of ballistic corona. So over the years, we sort of pondered various ways of addressing that. So one option is to just purely use a Boltzmann description for the whole system, because we know that the Boltzmann equation is exactly right in the corona, and we also know that the dense limit of Boltzmann is always just fluid dynamics. So in principle, solving a Boltzmann equation is a sort of inefficient way of solving the Navier-Stokes equation. The trouble with that idea is that in kinetic theory, the equation of state and the transport coefficient are not inputs, they're kind of outputs. And in particular, it's actually hard to construct a kinetic description that has a non-trivial equation of state. But because the acceleration of the fluid comes from gradients of pressure, if you want to do this quantitatively, you really need to use the exact equation of state, the one that was actually measured in experiment. Another option would be to combine a fluid dynamic description of the core with the Boltzmann description of the corona. That's in principle doable. There are fields of physics like the heavy ion game where this is done, but it's actually kind of complicated because you need to run codes and you need to have some kind of scheme that can convert fluid cells into particles and particles into fluid cells. So it becomes very complicated and it becomes very difficult to check that what you're doing is actually right. So the scheme that I eventually hit on hinges on something that I mentioned earlier, that in principle, fluid dynamics is motion of conserved charges, and they dominate at long distances and long times. And that means in particular that you can always take a fluid dynamic description and just randomly add equations of motion for conserved charges. And if you're in the fluid dynamic limit, it actually makes no difference at all. They don't modify the overall equation of motion for the system. However, if you add suitably chosen non-conserved quantities, you can use that to make sure that the hydro gracefully exits to various limits. In particular, you can add non-conserved charges that become conserved in the ballistic limit to ensure that the ballistic limit is reproduced. And so we found a set of moments of the Boltzmann equation that ensures smooth transition to the ballistic limit. And effectively, what it ends up being is sort of anisotropic moments of the energy density. So instead of just a single conserved energy density, I'm now propagating several moments of the energy density that are typically not conserved, individually not conserved, but their sum is conserved. It's the ordinary energy density of the system. And these Cartesian components of energy density, they become separately conserved in the ballistic limit because now there's no more scattering. So this is then formally a set of equations which has the property that if the collision time is very small, it's just a complicated way to write the Navier-Stokes equation. But if the collision time is very long, it becomes completely ballistic. And so I took that description and I checked it out by comparing it to an exact a numerical Boltzmann solver. So I asked a colleague who has such a Boltzmann solver to just run the unitary Fermi gas at very high temperatures where it's just purely two-body collisions and compute precisely this kind of observable, the aspect ratio over the formed cloud as a function of time. And so the dots here are the output of a Boltzmann solver for different initial temperatures. And the lines are this hydro plus plus, so a hydro code with additional non-conserved charges. And the agreement is really shockingly well. So effectively, I have a fluid dynamic equation, so an equation that just propagates conserved densities that exactly reproduces the Boltzmann equation without any free parameters. So I take this as evidence that I'm now simulating the dilute part correctly and that in the dense part, I can just use whatever equation of state and transport coefficients I would like to use. So another check that I did is that I took the data from the Thomas group. So again, initially that was 2002. There was a kind of first update in 2010. That's a paper in Science, slight improvement over the original data. Again, it's this aspect ratio as a function of time for a bunch of temperatures significantly above TC. So the lowest temperature is 0.8, which is sort of 5 times TC. And the highest temperature is actually something like 15 times TC. And so I took my hydro solver and I put in a quantum viscosity that's proportional to MT to the 3/2. So that's the expected high temperature behavior. And I treated the overall coefficient as just an independent fit parameter. So the dots you see is actual experimental data at different temperatures and different times. And these bands is a hydro fit, where the band is roughly what I consider the sort of statistical uncertainty in this fit parameter. But all 3 bands just correspond to a single value of eta naught. So all of these data are just fit by a single number. And that single number is something, it's written down here, it's 0.282. And what is amusing, it's the high temperature limit. So I can try to compare it to theory. And the theory prediction in that limit is 15 divided by 32 root pi. That works out to be 0.269. So you can see that these two numbers are within a few percent of one another. And I actually consider that kind of remarkable. There are not that many systems where you can really do a sort of first principle parameter-free calculation of some kind of transport coefficient, perform an experiment, and the two actually agree within a few percent. So that to me was actually pretty stunning, just how well that works. So we sort of have a high temperature baseline now, and we can try to push it to the lower temperatures. So this is yet another incarnation of the Duke experiment. So that's this Joseph et al., which is now from 2016. So what was done in order to do it better, so this is, if you wish, a sort of second or third generation experiment. Number one, the cloud was now imaged from 2 sides. So you can see all 3 radii, and indeed the trap was deformed in all 3 directions. So there's non-trivial dynamics in somehow 2 transverse directions. And it was also, in principle, one can measure the full time dependence, but the evolution of this thing is actually kind of slow. As you can see here, this actually didn't have any units on it. So you see that this actually takes several milliseconds to evolve. So what John decided to do is, here's the picture again, is to just measure it at a fixed expansion time, which is actually relatively short. So he gets better pictures at these short image expansion times. And instead of measuring the ratio of long to short, he measured the ratio of the 2 transverse radii, which differ by sort of factors of 2 or 3. So in that direction, the evolution is a little bit faster and the data are a little more accurate. So this is now data for this aspect ratio at a fixed time, but for different initial energies corresponding to different initial temperatures. Now you see that these error bars look larger, but it's effectively a blow up of the previous plot. So these error bars are actually quite a bit smaller than the previous error bars if you put them on an expanded scale. So in this variable energy in units of the Fermi energy, the transition temperature is right here. It's, I think, 0.61. And you can see that the expansion data actually seem to have a little bit of a break there. So it looks like you can see the phase transition in the expansion data, that there is something going on potentially in transport. But as a first go, I didn't try to fit anything below TC because that wasn't yet superfluid hydrodynamics. So the fits that you see on this plot are all strictly above TC. Now, in principle, I should fit the full functional behavior, but as a first go, I tried a sort of virial expansion. So there's the leading order MT to the 3/2 term, and I just tried to add a bunch of corrections to this that are now dependent on the density. So that involved this expansion parameter n lambda cubed. So lambda cubed is just the de Broglie wavelengths cubed. So this is the fugacity of the system. This term will automatically become small at high temperature, and it will become more and more important at low temperature. And these fits are now simply fits to the data involving more and more terms. So this is just the leading term, keeping the next term, keeping the term after that. And there's a little miracle that happens, which is that ordinarily fugacity expansions don't really converge all that well, but this one converges remarkably quickly. I really only need 2 terms. The third one is already totally consistent with 0. I have no idea why the transport properties look so smooth in fugacity, but that's just something that we find. Okay, so here's now what that fit looks like. So this is eta over n, so viscosity in units of density, or viscosity in units of entropy density, as a function of T over T Fermi. And T over T Fermi, the phase transition is now at 0.17, and it's this red band that somehow might fit, so the fit just terminates at Tc. The data points that you see in this plot, by the way, was an attempt by John. He had a sort of poor man's theory to analyze that himself, and you can see that it kind of agrees at high temperature. It doesn't agree so well at low temperature. The dashed lines you see in the plot on the right-hand side is the kinetic theory. So this dashed line is the high temperature kinetic theory. This dashed line is the low temperature kinetic theory. So again, that was my comment that looks super steep. The actual data, at least above TC, they seem to sort of flatten out. Again, this band is a kind of error band. So what I find is that number one, you can again check what the leading coefficient is at very high temperature. This is now an even better fit because it doesn't just take into account the leading behavior, has subleading behavior in it as well. So now the coefficient is 0.265, so that's even closer to the theory that's now within a percent or so. And directly at Tc, eta over the density becomes of order 0.4. Eta in units of entropy density is about 0.5. So again, that's this funny fact about the unitary gas, that directly at Tc, the entropy per particle is actually pretty darn close to 1, for reasons that I also don't totally understand. Now, what we did is a totally primitive, blind attempt to just take the theory, ignore superfluidity, and just use the same method below Tc. So effectively, you're somehow assuming that the superfluid and the normal fluid stay totally in phase, and the dynamics of the normal component is actually unaffected. So ultimately, that's not right. It should be improved. But if you just do this, then indeed you do conclude that the data seem to have a little bit of a break directly at Tc. And so if you just blindly try to fit this, you would conclude that there is a pretty significant drop in the viscosity as you go through Tc. So it starts to drop pretty steeply. Again, these different curves are effectively a sort of error band. This is the actual data now shown as a function of temperature, where effectively what used to be a very narrow range in E over T Fermi and T over T Fermi now becomes a wider range. And again, there's a little bit of a hint of a discontinuity. So the aspect ratios go up, the viscosity would appear to go down. Okay, so we're still working on doing this right. So to perform the analysis, really using the two-fluid hydro. So I have a little bit of a suspicion that this apparent drop in the viscosity is maybe a dynamical effect that has nothing to do with viscosity, but is really some sort of decoupling of the normal and the superfluid components of the fluid, that they start to move effectively independently. So we have to check that, and we're currently working on that. Of course, Martin was talking about the fact that these days there are all these beautiful box potentials. So we, of course, interested in checking ultimately what is the best way to do this. Should we work with the boxes and sound modes, or should we work with the expanding systems? The expanding system, I mean, the boxes in principle seem far superior because now you don't have to unfold the density dependence. You have the whole system at the same temperature and density. That clearly seems much better. There are some downsides. There's a sort of nice aspect of the expanding systems, which that the actual experiment is done with, everything turned off. I mean, other than the magnetic field. So all the light beams are turned off. So the system is remarkably low noise and low loss, so that even very small viscosities can potentially be accurately measured because you're not losing any particles or anything. So I think it's actually not necessarily a done deal that the box potentials are far superior because there's so much stuff going on. But in any event, we'll obviously figure that out. And clearly, we're also interested in a variety of other transport properties. I've actually done some work, which I didn't show here, on spin diffusion. And of course, indeed, ultimately, we're interested in also pinning down thermal conductivity and bulk viscosity near unitarity. and in a perfect world also see whether the thermal conductivity in particular should really have interesting critical behavior in the vicinity of the phase transition. So we're interested in seeing that. Well, thank you so much, and I'm glad that seemed to have worked out.
All right, thank you very much. Time for some questions? All right, Martin?
Thomas, thank you for a wonderful, very educational talk. Of course, you have to tell me what you meant by so much stuff going on into the boxes. It seems it's pretty pristine when you have, when the atoms sit in the dark most of the time. In the inhomogeneous situation of the harmonic trap, when you expand, you have this issue of the crossover from hydrodynamics to ballistic. So
yes.
Would you say that's a worse problem to have than, I don't know. I don't know what the problem with the box is.
Yeah, I mean, well, number one, of course, I shouldn't have commented. I mean, that's purely an experimental issue, which I have no real understanding of. So in some sense, I should just keep my mouth shut. That is the most appropriate way to handle this. So indeed, there is a theory problem with the expanding systems, which frankly, I mean, took us 10 years to fix. And I was always concerned that we would never be able to fix it well. But surprisingly, I think we actually have gotten that under control, and we can now do that well. So what I meant is simply that I've actually have been analyzing. So John also has a little box, and he played some games with his boxes. And I have been analyzing that using fluid dynamics. And there's a sort of new set of problems that arises because now the thing has pretty sharp edges. And there's a little bit of an issue, at least within fluid dynamics, what exactly you should do at the edges, what kind of boundary conditions you should impose, whether you should really take these very steep density gradients seriously, because potentially that produces little shocks and so on, which you don't really think exist. So I'm not sure. I mean, the boxes are beautiful, and we should, of course, do it, and that may ultimately indeed be far superior. But okay, I don't think it's necessarily totally settled.
I have a completely different question on the viscosities, understanding the various viscosities. So zeta 3, Boris Vistonov tells me that is 0 if you don't have quantum turbulence. So that would be interesting to hear your opinion on. The eta,
that comment, I saw that comment in your talk, and I actually don't know what he means by that. So the
if you don't have vortices to scatter off, he says, then there's no friction between the normal and the superfluid, which sounds to me.
I mean, so what is, I mean, I wrote down the formula. So number one, this coefficient has been estimated, and I think it's definitely not 0. And it would seem to multiply just the divergence of the difference between the two velocities. Now, of course, there are flows where that divergence may be 0, but I think, for example, it's not 0 in second sound. And, as has been checked in the days of helium-4. And indeed, we've played a little bit, again, we're somewhat not quite ready to show that, but we've played a little bit with expanding systems where indeed, in general, even without, I have no vortices in these expanding systems, and the divergence of Vn minus Vs is not 0. I mean, it may not be large enough to be truly important, but I don't think it's 0. I don't totally understand that comment.
Cool. Interesting. I had 2 more viscosities I wanted to ask questions about. One is the eta is, you said 1/t to the 5, but if you allow for 3 phonon processes, it should be 1/t, which is much smoother and less steep. So I'm sort of more sympathetic to 1/t. that would be that. And the last question, and then I shut up, is whether you can simply add viscosities like you had in one formula of the helium situation with the rotons and the phonons, or whether one should rather add things that go like the inverse of viscosities, like rates.
Yeah, that's a good question. And I pondered that many years ago, and now I'm not sure if so generally one should actually, if you have one quasi-particles and it's subject to a bunch of different scatterings, then you should definitely add them in inverse. But if you have entirely different processes, it becomes a little less obvious, and you really have to carefully solve, kinetic equations for coupled motion. So indeed, I showed this formula, and I'm sure at some point I knew where it came from, but right now I'm actually not sure why that's the correct way to write it. But I think you can find that formula just in Kolotnikov's old book.
One more question.
So I had a question about the viscosity curve you showed where you compared your extraction of the viscosity to the Thomas experiment.
Yeah.
And near TC, your values were a bit lower than the values, almost by a factor of 2.
Yes.
So the question I had was, do you think you have control near TC or only maybe twice of TC or something like that? Do you trust this factor of 2?
So, I mean, just like I, as a theorist, shouldn't comment on what is the superior experiment, I think as a theorist, I am allowed to say what the superior theory is. So, I mean, what John did in his paper is perfectly fine. And I mean, as a sort of first shot, and I actually, we talked about how to do this without invoking some more complicated simulations, but it's not a reliable way to do it. So these great data points, you should view them as having a completely uncontrolled systematic error. And in fact, he effectively, at high temperature, he kind of by hand aligned them with the expected kinetic behavior. And so the fact that this agrees at high temperature is in some sense not an independent confirmation, because John's theory was sort of designed to work like that. So, so I actually tend to believe that this error band that I show there is a believable error band. I mean, it's always possible that there's some sources of systematic error that I missed, but I don't actually think so. I think that this is believable. And I think since this is just hydrodynamics, I'm allowed to use it all the way down to TC. And so I tend to believe in the red band all the way down to TC. As I mentioned, the thing that I don't believe in is, okay, now I just run it below TC. And now my hydrodynamic theory is just really not right, or it's only right if a number of miracles occur, like the motion of the normal and the superfluid flow stay exactly in phase or something like this. So this here is uncontrolled, but this here I tend to think is controlled, and you should believe the red band, not the blue dot, not the gray data points.
Okay, thank you very much, Thomas, and thank you, everyone. Let's have one more. Okay, so we'll have a slightly delayed coffee break. Please be back by 10:30 for the start of the next talks. Thomas?
Yes?
I make a request for you. Could you possibly record the introduction of your talk using Zoom, and then I'll give you a place to upload that, and then I'll splice it together with what we actually thought.
Mm-hmm. Can you let me know? I mean, if you just send me an email letting me know, I know that at some point during the talk it came on, but I don't know exactly where.
Sure, we'll do that.
What slide that happened, I can try it.